Welcome. As a review slash reminder of what we had been doing the past couple days before AP testing and other events occurred, I'd like you to take a couple minutes to look at this warm up and answer the questions on different limit notation, function notation, and graph analysis. At this point, you can pause the video and jot down your answers to these questions and then restart it again when you are ready for answers and explanations. Welcome back. Let's see how you did. First question, f of negative 2. We want the value of the function at x equals negative 2. If you look at the graph where x equals negative 2, you can see a vertical asymptote indicating that the function is undefined at that value. Next problem, the limit as x approaches negative 2. Notice without the superscript plus or minus, that means we're talking about a two-sided limit. We need to consider what happens as we approach negative 2 from both sides. As we approach negative 2 from the left, and as we approach negative 2 from the right, you can see that these values are going in opposite directions, meaning the single one-sided limits are not equal to each other, so the two-sided limit does not exist. Next question, f of 0. Again, looking at your graph, locate where x equals 0, which would be on the y-axis. You can see there are two different possible values here. This value has an open circle, indicating that value is not included. This point is a filled-in circle, indicating that that is the value of the function at x equals 0. So my answer, f of 0 equals 4. Part D, the limit as x approaches 0. As I approach 0 from both the left and the right side, you can see those one-sided limits are not equal to each other, so the two-sided limit does not exist. Next problem, we're looking for the value f of 2, value of the function at 2. Again, on my graph, I'm going to locate the place where the x value is equal to 2. If I follow that up to the function, you can see there's an open circle at that point. So that tells me I have an undefined value at x equals 2. The limit as x approaches 2, two-sided limit, as x approaches 2 from both the left and the right-hand side, you can see they're zeroing in on the same value of about a half. Next problem, as the value of the function at 4. At 4, if you follow on the x-axis to find 4 and go up, you can see there is a filled-in circle at a y value of 2. So that is the value of the function at x equals 4. And then the last problem from this warm-up, the limit as x approaches 4. As I approach 4 from the left and from the right side, you can see both of those one-sided limits are increasing forever to infinity. Today we are going to talk about finding limits algebraically. Past couple days we've looked at analyzing limits, evaluating limits based off of graphs, based off of tables. Now we're going to look at an algebraic approach to evaluating limits. You can see on the screen what your assignment will be. That will come back at the end of the video as well. But it is there for you to look at now too. This is really weird, talking to a class of no students. All right, so on the top here, you have some different properties of limits. All of these are listed in your book as well. I have them here as a reminder. I think they're probably assumptions that you would make anyway, but wanted to, at least for a little bit, talk about them here. We're just saying if we have two functions, f of x and g of x, that, for example, in this first, see, I'm pointing, but you can't see. In this first rule, the sum rule, the limit, if I take the limit of the sum of two functions, It's the same as taking the limit of each function individually and then adding those together. So really easy example, let's say I have like the limit, I'm going to make up a number here, as x goes to 0 of x squared plus 3x, right? This function, one function really is the sum of two separate functions. So this first rule is saying if I want to take the limit of a sum of two functions, I could do that by taking the limit of one separately and then adding the value that I get for the limit of the other. Pretty much I can split apart that addition. Difference rule, similar idea, but with a subtraction sign. If you have the difference of two functions and you're evaluating the limit, you can find the limit of one and then subtract the limit of the other. Product rule, same thing, you can split that apart, multiplication apart. Constant multiple rule, if you have a constant times a function, you can bring that out constant out front and evaluate the limit. So kind of like what I had up on the board, the limit as x goes to 0 of 3x maybe. That 3 is a constant, so this is saying I could bring the 3 out front and just evaluate the limit of x. Quotient rule, I can split limit of the quotient of two functions apart. Again, the only caveat on this is that the limit of the function you're dividing by can't be 0 because we can't divide by 0. And then the last property of limit on there is the power rule, saying if you have a function being taken to a power, you can evaluate the limit first, or you could evaluate the power and then the limit. Again, just as long as the power you're raising the function to, r and s are integers, and we can't divide by 0, so the value of s can't be 0 either. All right, so a couple of methods for evaluating limits algebraically. The first is the most straightforward, the one you're always going to want to try and use first. Unfortunately, it won't always work, but the first thing you're going to want to try to do in pretty much every situation is try direct substitution. Directly substituting a value into your function and evaluating. Some examples over there on the left side, you will use direct substitution in polynomial functions, linears, quadratics, cubics, radical functions, as long as it doesn't cause you a domain error, you have a value that's in the domain, exponential functions, rational functions, again, as long as you're not dividing by 0. Pretty much in a nutshell, anytime that c is in the domain of the function, you can directly substitute in and get a value. For example, let's take a polynomial function. The limit as x goes to 1 of the polynomial function 2x squared minus 3x plus 1. To evaluate this limit algebraically, I'm going to directly substitute a 1 in for x. I want to know what's happening as x approaches 1. I know this polynomial function is continuous, so I know whatever the value is at that point, that the one-sided limits also have that value, which means my two-sided limit would exist whatever the value is at that function. So to evaluate this limit, I am going to directly substitute in a 1, 2 times 1 squared minus 3 times 1 plus 1. So 2 minus 3 plus 1. The value of that limit should equal 0. Okay, another function for you, rational function this time. You are not going to always be able to substitute into a rational function. In this example, we will, and I'll talk about what's different about this one. So let's look at the limit as x goes to 2 of the rational function x squared over x plus 1. I can directly substitute a 2 into this function. If I substitute a 2 in, I'll have a denominator of 3, and it's perfectly legal to divide by 3. The only value I could not directly substitute in for this function and evaluate a limit would be an x value of -1, because that would cause me to divide by 0. Can't divide by 0, we'd have to try a different algebraic method to get an idea of what that limit would be. But in this case, like I said, we can directly substitute in a 2.